Hello everyone. Today we are going to discuss about Root Locus Plot in control systems. Myself, Dr. Kevson. At the end of this video, students will be able to construct the Root Locus Plot. The Root Locus technique was introduced by W.R. Evans in 1948 for the analysis of control system. It is a powerful tool for adjusting the location of closed loop poles to achieve the desired performance by varying one or more system parameters. This block diagram shows a simple closed loop block diagram. From this we can find the closed loop transfer function, that is C of S over R of S. In this transfer function, denominator polynomial, it is nothing but characteristic polynomial. So the poles of the transfer function are roots of the characteristic equation. If you are equating the polynomial equal to 0, so that is a characteristic equation. From that we can find the roots. Those are nothing but poles of the transfer function. So this characteristic equation, from this we can find that is if it is satisfying the magnitude and angle conditions, then only it is we can construct the exact shape of root locus. The root locus is the locus of the characteristic equation of the closed loop system, as the parameter vary from 0 to infinity. Magnitude condition from the characteristic equation, that is mod g into h is equal to 1 over k. The angle condition, that is angle of g into h, is nothing but 180 degrees into 2q plus 1. Shows that always angle is odd multiples of 180 degrees. For the construction of root locus, we have to follow some rules. Those are construction rules for the drawing root locus. First one, root locus is symmetrical about the real axis. Always it is symmetrical about the real axis. And second one, root locus starts at open loop poles and ends at open loop zeros. That means from this we can find the open loop poles when k equal to 0 and open loop zeros at when k equal to infinity. We can find from the transfer function. And third one, number of branches of root locus is equal to number of closed loop poles, or we can say roots of the characteristic equation. So the number of branches terminating at zeros at infinity. Rule number 4, it is a testing point whether the root locus it is on the real axis or not. Depending upon the poles and zeros on the real axis, we have to take some test points. You need to see from the test point to the right of that how many poles are there, how many zeros. Some of the poles and zeros is odd number, it is a part of real axis, or if it is even number, it is not part of root locus. Generally it shows with bold line. And rule number 5, from this we can find number of branches will become asymptotic to a straight line. That means here from this we can find the centroid as well as asymptotic lines. Centroid is nothing but asymptotic lines meeting point. From these two formulas we can find, first one is centroid. So that is the ratio of sum of the open loop poles minus sum of the open loop zeros by number of open loop poles minus number of open loop zeros. From this we can find centroid, and theta is asymptotic angles. 180 degrees into 2k plus 1 by n minus 1, where k equal to 0, 1, 2 and so on, n minus m minus 1. And rule number 6 is breakaway or break-in points. Generally, breakaway points exist between two poles and break-in points exist between two zeros. These breakaway or break-in points can be found by using the simple formula dk by ds is equal to 0. Rule number 7, the angle of departure or angle of arrival can be found by using another simple equations. The angle of departure exists only if the transfer function is having complex pole. Angle of arrival exists only if the transfer function is having complex 0. From these two formulas, you can find angle of departure and angle of arrival. Angle of departure of a locus from complex pole, we have to take one pole, complex pole as a reference. Phi p is 180 degrees minus sum of the other remaining pole angles to the reference pole plus sum of the 0 angle to the reference pole. Similar way, we can find the angle of arrival if the complex 0 exists in the transfer function. Rule number 8. The root locus passes the imaginary axis. The crossing point and corresponding gain can be found by using Routh-Hurwitz criterion, and also by using another method we can find the imaginary axis crossing point by substituting s equal to j omega in the characteristic equation and equate real and imaginary parts to the 0. From that also we can find j omega, that is imaginary axis crossing point and also corresponding gain. By following these rules, we can construct the root locus. These are the steps we can follow. These steps we can draw the root locus. Step 1. Whatever the transfer function given, we need to take as a characteristic equation of the closed loop transfer function, that is 1 plus k into g of s into h of s equal to 0. Second is find the poles and zeros. Mark poles and zeros in the complex plane, that is S plane. X represents poles and 0, that is a small circle, represents zeros. Real axis segments, that is by using test points we can find that whether it is on the real axis or not. Next, we can find number of asymptotes, asymptotic angles, and asymptotic angles missing point, that is nothing but centroid, by using those formulas. And remaining, that is angle of departure, angle of arrival, depending upon transfer function. If necessary, you need to find, otherwise no need to find those angle of departure and arrival. Breakaway or break-in points you can find by using dk by ds is equal to 0. And after finding those roots, again substitute those values in expression k. If k is positive, then only breakaway point or break-in point. Otherwise, no breakaway or break-in points. Imaginary axis crossing points by using either RH criterion, Routh-Hurwitz criterion, or simple method, that is substituting s equal to j omega in the characteristic equation, separate real and imaginary parts, equate to 0. From that also we can find this. Substitute all this in graph, that is a normal graph paper. We can construct, that is we can sketch the root locus. Thank you all.